So we are now recording after I've given the class who was here today all the answers to the first exam. Right, carbonyl reactivity. So here is a generic carbonyl structure. R is going to be anything, could be a benzene ring, could be something carbon, could be an alkyl group. And then Y we're going to choose because we love BYU, and it can be basically any number of things that I'll tell you in a little bit. Carbonyl reactivity is dominated by the existence of this resonance structure in which you move the electrons, the pi electrons, from the carbon-oxygen pi bond, and you put them out on the oxygen with a negative formal charge on the oxygen and a positive formal charge on the carbon. And that tells you that the carbon-oxygen bond is polarized. You should already expect that to be the case because oxygen is more electronegative than carbon. But this other resonance structure is a minor but significant contributor to the overall reactivity of the carbonyl compound. It tells you that you expect the carbon to be electron poor, which we're going to indicate with that little Greek letter delta, meaning a small amount increment of partial positive charge, and the carbonyl oxygen should have a partial negative charge on it. Understand, you know this now, that resonance structures are both accurate descriptions of the molecule, but in and of themselves they're incomplete. You need all of them to get the overall picture. So you expect carbonyls to be electron poor on the carbonyl carbon, but to be electron rich on the carbonyl oxygen. That's really important. That's going to govern a lot about how these molecules behave. We're going to talk a lot about the influence of what this R group, or sort of Y group is, on the reactivity of the carbonyl compound. We're going to ask questions like, is the Y group a good electron donor? What do we mean by that? Well, some groups are good at sharing electron density and others are not. These are concepts that you probably are already familiar with. One way that you can be a good electron donor is via resonance. So let me give you an example of something that Y can be that would be a good resonance donor. I'm going to draw for you the structure of a carbonyl molecule called an ester, where the Y group is this methoxy group here, right? And I'll just abbreviate that. Sometimes people abbreviate methoxy groups, CH3O, as just MEO. Hopefully you'll get used to that. The oxygen has a lone pair on it. And what I showed you above for the resonance structure of this ester carbonyl compound still holds. There's still a resonance structure where a positive charge is on the carbonyl carbon, but now look what we can do. That Y group has lone pair electrons on it, and they can donate into the positively charged carbon, creating a new oxygen-carbon pi bond with now a positive formal charge on that oxygen and a negative formal charge on the carbonyl oxygen. What do you think that does to the carbonyl carbon? What does that extra resonance structure tell you? Is that carbonyl carbon more or less electron poor than it would have been without the lone pair on that neighboring oxygen? Less electron poor. Yeah. Resonance electron donation makes the carbonyl carbon less electron poor or less electrophilic. So you would expect the ester to be not as electrophilic as a related carbonyl carbon that lacks that lone pair. As an example, so we'll say the ester is less electrophilic than an example of a carbonyl compound that lacks a resonance electron donating group is the aldehyde, where the Y group is just a hydrogen, no lone pair, no possibility of resonance donation of electron density into the carbonyl carbon in the aldehyde experiences the full impact of that partial positive charge. So you'd predict aldehydes would be more reactive than esters. And in fact, that's the case in chemistry and in biology. All right? Another example of electron donation is something we're going to call the inductive effect. The inductive effect is related to electronegativity. So how can you donate electron density via electronegativity? Well, the thing that does the donating simply must be less electronegative than the thing that does the accepting. Classic example of this would be a ketone. So let me show you the structure of a ketone versus an aldehyde. In a ketone, that Y group is something carbon-based. I'm going to draw that same resonance structure for you here. And I want to talk about how the methyl group in the ketone is an electron donating group. The way to explain this is just to look at the hybridization of the carbonyl carbon, which is sp2, versus the hybridization of the methyl group carbon, which is sp3, right? Which of those hybridizations has higher percent S character? That is a 351 question. Go. sp2, right? 33% instead of 25%. S orbitals hold electrons closer to the nucleus, lower in energy. sp2 orbitals are therefore more electronegative, because that's actually what electronegativity means, how low in energy electrons are on that atom. sp2 carbons are more electronegative than sp3 carbons, so in a ketone, the sp3 carbon actually donates electron density towards, I'm going to use a little dipole symbol that you may have seen in general chemistry to indicate that the less electronegative sp3 carbon donates electron density through the sigma bonds to the sp2 carbon. So, comparing the aldehyde to the ketone, okay, an sp3 carbon is less electronegative than a hydrogen, so electron donation is better for the ketone than it is for the aldehyde. Therefore, you would predict that, again, the ketone is less electrophilic than the aldehyde. And in fact, you can observe that all the time in chemistry, okay? So the identity of that Y group on the carbonyl is going to be absolutely crucial. So with that in mind, and before we talk a lot about reactivity, or rather the kinds of reactions that these molecules can undergo, I want to spend just a minute to survey most of the carbonyl compounds you will encounter in this class and in biology. And we're sort of going to rank them in terms of reactivity. And I'm going to put them in 3 or 4 different groups, starting with the most reactive, most electrophilic, to least electrophilic. And some of this is going to set the foundation for things you're going to learn in biochemistry. Reactions that you'll see in biochemistry are going to make sense because of some of the things that we'll talk about today. So, if you were to put these things in rank order, I've already done some of this for you already because we have aldehydes up here, and we've put ketones a little bit down the list, but let's just focus on aldehydes. This is sort of group 1. In group 2, you have esters. And I guess I'll show you the structure of an aldehyde. Now, I'm going to show you group 3, which is a functional group where instead of an oxygen, we put in a nitrogen. This is a functional group called an amide, and sometimes we will call this portion of that functional group an amide bond. Other times later on in the class, we will call that a peptide bond. Now here's the first question. Well, I've asked other questions. So the nth question of the class, which is, why did I put the amide as lower in reactivity than the ester? Because I am the professor and I know everything, and therefore it is true. No. Why?
Because nitrogen is less electronegative than oxygen.
Okay. So that is a true observation, a fact. Nitrogen is less electronegative. I rarely have the patience to write out electronegative in its entirety. Often I abbreviate it like that. Nitrogen is less electronegative than oxygen. Okay, so what? Why should that make the amide less reactive? Yes? Okay, the leaving group is less stable. We haven't even gotten to leaving groups, but you're right. We're going to get there. As we think about carbonyl reactivity, we're going to pay special attention to where this Y group could leave and be replaced by something. You are right that OR minus as a leaving group is a better leaving group than RNH minus, for sure. You can tell that just by thinking about OR minus versus NHR minus, then thinking about their conjugate acids, as you learned to do in 351. As Celine Dion sings, is it all coming back to you now? You guys don't know that song. That was a song from my day, years and years and years ago. Look it up. Stick to the Star Wars references, Flyboy. Yeah, so you can tell that NHR minus is a poorer leaving group than OR minus because its NHR minus is less stable. You can tell that by comparing the pKa's of their conjugate acids. Make sense? That's a 351 argument. Okay, good. What else?
Does it have something to do with the fact that if you draw a resonance structure, the N will now be sp2 hybridized?
Does it have to do with the hybridization of the nitrogen in the resonance structure? Not necessarily with its hybridization, but you're on the right track to be thinking about resonance structures. I'm going to go back to what I showed you on the earlier screen about how the oxygen donates electron density via this resonance structure. And then I'm going to point out that nitrogen can do that too. Now I want you to think about whether you should expect nitrogen. I'll just draw that other resonance structure. Oops. And I'll do that for the ester as well, just so we can make a comparison. Which of those is a better resonance structure, and how can you tell? Another way, that's the same question as asking which is more willing to donate its electrons, the oxygen or the nitrogen? The nitrogen. The nitrogen is less electronegative than oxygen. That means its electrons are held a little bit higher in energy where they are more available for sharing. Okay, nitrogen is a better donor because it's lower electronegativity. That means that this resonance structure is a bigger contributor for the amide than it is for the ester. And therefore, the amide is less reactive than the ester. Better donor, smaller delta plus on the carbonyl carbon, less electrophilic. Okay? This is really important because the workhorses of biochemistry are proteins that are individual amino acids connected by this kind of bond. They are actually made from precursors that are called aminoacyl tRNAs, which are esters. Biology uses an ester, a more reactive precursor, to make a product which is less reactive, going downhill in energy. Okay? All right. Let's see. And then fourth on the list, we're going to put something that actually you've seen before. This is the conjugate base of a carboxylic acid. This is called a carboxylate. Why would this be less reactive than the amide? Go ahead.
That oxygen wants to get rid of that charge.
The oxygen does have a full negative charge on it. That's going to be a better donor than the neutral amide or than the neutral oxygen, right? And in fact, you've grown up in organic chemistry learning to draw this alternative resonance structure. You should already be used to thinking of that negative charge as delocalized equally on both of those carbons. The carboxylate is not very reactive at all. It's sort of an endpoint. Okay? Let's scroll up the list a little bit more. We'll have some more to say about the conjugate acid of a carboxylate, but the reason, which is a carboxylic acid, the reason I'm showing you the carboxylate is that is the form of a carboxylic acid at the physiological pH of 7. So in biology, if you've got a carboxylic acid, it's usually in this form, and that's an important thing to realize. We'll have some more to say about carboxylic acids in organic chemistry in a little bit. At the top of the list, I want to include some other things that are very highly reactive, some of which are found a lot in biology, others of which are only found really in the lab that we use from a synthetic point of view. We'll stick with the biological ones to begin with. I'm going to just, for now, if it's okay, I'm going to include aldehydes and ketones in the same category, even though you know and I know that aldehydes and ketones are different and that the aldehyde is a little bit more reactive than the ketone. Whoops, let's see, need to rearrange. I wanted that, no, that, there we go. Slide it down a little bit. Sorry if the notes aren't aesthetically pleasing. It's sort of hard to do this on the fly. Right, so another molecule that you'll encounter in biology, not so much in the textbook, but you'll encounter it a lot later on when we start talking about metabolism, is something called a thioester. A thioester is the sulfur version of the ester, but notice I didn't put it down with the ester in terms of reactivity. I put it next to the aldehyde. Why do you think the thioester might be more reactive than the ester? Your instinct is going to be to say it has to do with electronegativity. That's the wrong way, actually. Sulfur is less electronegative than oxygen, right? So if it were about electronegativity, you'd think, oh, maybe that sulfur isn't pulling so hard against that carbon. Maybe it's more able to donate its electrons. Why is the thioester up so high in reactivity? Yeah, go ahead.
My guess would be what someone else was talking about with leaving groups.
Leaving group ability.
The thioester, the sulfur group can leave.
Okay. Right. We've talked before, we talked a little bit, you learned a lot actually in 351 about leaving group ability. And though I haven't said a lot about it today, it is also one way that you can rank the reactivity of carbonyl compounds or related ones. The argument here is Sr minus, whose conjugate acid is a thiol, and if you look this up, would have a pKa of 8, is a better leaving group than OR minus, which you saw with the esters. Conjugate acid is the alcohol, pKa of 16. Remember, pKa units are factors of 10, so you're looking at 100 million times better of a leaving group Sr minus is than OR minus. So that's part of it. Why? Why is Sr minus a better leaving group than OR minus? Yeah, go ahead.
Is it because sulfur is a bigger atom than oxygen?
Yep. Sulfur is a bigger atom than oxygen. Size is bigger for sulfur. As you go down a column of the periodic table, in the same column, size increases. The larger an atom is, the more space it spreads out its electrons. Electron delocalization is a favorable thing. Oh, if you want to know more about that, we could go down a rabbit hole, but when I try to do this, people tell me to stop. It has to do with electron kinetic energy and the second derivative of the wave function. Doesn't that sound exciting? nerd alert. If you want to know more about that, there's an optional MO theory study guide that you can read on the content page of Learning Suite that delves into that. Yes, in general, the larger an atom is that holds electrons, the more those electrons are spread out. That's a stabilizing effect. The size also makes it so that sulfur is not as good. The size makes it so that sulfur is not as good of an electron donor. And the real explanation for that is a little bit more complicated than we need to delve into today. The larger an atom is relative to another atom, the more poorly their orbitals overlap. Resonance actually is about orbital overlap. So the sulfur is not as good of a resonance electron donor, and that makes the thioester less stable than the ester. Okay? Also on the list for things that are highly sort of reactive about the same extent as aldehydes and thioesters are a class of molecules called acyl phosphates. You won't encounter these until we get to metabolism really, but I mention them here. And it's a toss-up at pH 7 as to whether both of those oxygens are negatively charged or one of them's an OH group. This is reactive for the same reason that the thioester is reactive, is because what I'm highlighting in green is a good leaving group. And in general, carbonyl compounds where we have good leaving groups attached to the carbonyl carbon are reactive. Acyl phosphates, stay tuned, you'll encounter those a little bit later. We can also include on this list, since we're dealing with biology, things like ATP and ADP. They're not exactly carbonyls, but they sure look like it and act like it. And they act like they're carbonyls with good leaving groups attached. I'll have more to say on this later. Don't worry about it for now, but we'll come back to it, and you'll see that they fit in this same category. Finally, on the list, we can include things that are more sort of lab-only type chemicals. And now, if you were to shout out leaving groups, you would come up with good answers. If we let the Y group be Cl-, that's an acid chloride, and that's very reactive. And it turns out if we let the Y group be something like this, a carboxylate, which can leave as a negatively charged conjugate base of a carboxylic acid, that's called an anhydride, and that's basically on the same level of reactivity as the acid chloride. We're going to see that it's really easy in 352 to take a more reactive carbonyl compound and convert it into a less reactive one. It's more challenging to go the other way. All right, questions about that overall ranking? Yeah?
Could it be said that bigger molecules in general are better leaving groups?
Are bigger molecules in general better leaving groups? No. When we're talking about leaving group ability, it's always about the atom that has the negative charge. So you focus in on that atom. And in this case, the sulfur versus the oxygen. Size does matter for sulfur versus oxygen, but we're focused in on the atom that has the negative charge, not necessarily everything else. Okay, others? Yes?
There's a lot of molecules in the first category. Is there going to be a moment later on where we need to distinguish between those?
There's a lot of things in this top category. Are there going to be things later on where we need to rank them? Not necessarily the thioester or the acyl phosphate. However, you could predict pretty easily that the acid chloride would be, the chloro is a better leaving group than the carboxylate. I feel like that's a fair comparison, but yeah. Yes?
So is there less electronegativity equals more reactivity? Is that
Yeah, you're summarizing what we're talking about based on the principle of electronegativity. Thinking about the Y group, better donors, electron donating Y groups lead to less reactive carbonyl compounds. Okay? Poorer donating groups lead to more reactive carbonyl compounds. So in the case of the amide versus the ester, the reason they're similar in terms of their resonance structures, both the oxygen and the nitrogen are electron donating groups. Nitrogen's better than oxygen because nitrogen's more willing to share. It's less electronegative. Yeah? Would a carboxylic acid be basically about the same as an ester? No, and I'm going to tell you why not. The carboxylic acid is weird. The carboxylic acid is the conjugate acid of the carboxylate. Its chemistry is dominated by that acidic proton whose pKa is 4. In just a second, we're going to talk about what happens when a nucleophile encounters a carbonyl compound, and we're going to talk about what that nucleophile does. For most of these, the nucleophile is going to go where the partial positive is. That is, it's going to attack the carbonyl carbon. However, for the carboxylic acid, you've got another tempting choice. You've got this very acidic proton, and often nucleophiles will remove that proton first. Often, if we want to do chemistry with carboxylic acids, we're going to have to do something to deal with this proton first, and we'll get into that later. All right, let's talk about carbonyl compounds reacting as electrophiles. We've set this up already by telling you about resonance and the partial positive charge that is on the carbonyl carbon. And that's good enough for some people, and some people stop there. I find it useful to take one step further and try to understand what the orbitals in the molecule are doing. If you took 351 with some of my colleagues or from me, you may have some background in molecular orbital theory. If you didn't, that's okay. We're not going to go too in-depth, but what we do talk about will be useful and will help you remember reaction mechanisms. So for molecules in organic chemistry, we care a lot about what the highest energy electrons are in the molecule and what the lowest energy electrons are in the molecule. And all of 351 was designed to help you get some intuition for that. If you were to look at this aldehyde, what are the highest energy electrons in this molecule? There's controversy. Good. Some of you are saying the pi electrons. Presumably you're saying that because you know pi bonds are less stable than sigma bonds, so electrons in pi bonds should be higher energy than electrons in sigma bonds. Good. Those of you that said lone pair are thinking, hey, those are in an atomic orbital, not even involved in bonding. Bonding always moves electrons down in energy. Therefore, electrons that are not involved in bonding must be higher in energy than are the electrons that are involved in bonding, and that's right. So lone pair electrons, there's two of them, I'm only drawing one of them, on the oxygen are the highest energy electrons in the molecule. Those of us that talk about molecular orbital theory know that those electrons are held in an atomic orbital on that oxygen. What is it? It actually doesn't matter that much. You can think of it as an sp2 hybridized orbital if you want, that one of those lone pairs is sitting in. There are other ways to think about it too. So we'll call those highest energy electrons, they are in the highest occupied molecular orbital of the molecule, or for abbreviation HOMO, HOMO. The HOMO of the molecule is the lone pairs on the carbonyl oxygen. That means that if this molecule is going to react as a Lewis base or a nucleophile or an electron donor, the most reactive electrons react first. So you already know, looking at this molecule, if it's going to be a nucleophile, it's the lone pairs on the oxygen that do the attacking, right? The first and great commandment of 351 was, and of all organic chemistry, is nucleophiles attack electrophiles. The second is like unto it, HOMO attacks LUMO. Highest energy electrons on one molecule attack a low energy empty orbital on another molecule. Now, so if the carbonyl were to act as a nucleophile, What's it going to do? The lone pairs on the oxygen are going to do the chemistry. An example of this would be a simple proton transfer reaction that we'll see later on this semester. Bring an acid into proximity to a carbonyl compound. The thing that happens first is the carbonyl oxygen attacks the proton, breaking the bond between the proton and the A group, whatever it is. And that gives you a new bond between oxygen and hydrogen, and then you've got the conjugate base over here. Okay? That's an acid-base reaction, but you know where the proton's going to go. It's going to go where the highest energy electrons are. Does that make sense? This protonated carbonyl is called an oxonium ion. And protonating a carbonyl is one thing we're going to do when we need to soup up the reactivity of a molecule, when we need it to be even more electrophilic. The reason protonation increases how electrophilic this carbonyl is because it makes this resonance structure even more reasonable, right? Once the carbonyl is protonated, you got the oxonium ion, positive formal charge on the oxygen. I can draw a resonance structure where I take the pi electrons from that carbon-oxygen bond, I move them out onto the oxygen. Now the full positive charge is on the carbonyl carbon. Oxonium ions are more reactive than their conjugate bases because they increase the amount of positive charge that's felt on the carbonyl carbon. Let's talk about carbonyls as electrophiles. All right, so we've talked about their nucleophilic character. Now let's talk about carbonyls as electrophiles. When we come to electrophiles or Lewis acids, we are concerned about what is the lowest unoccupied or empty molecular orbital in the molecule. You may not be used to thinking about empty orbitals. If you're not, you should look at that optional MO theory study guide to get up to speed. But the basic concept is anytime I mix two atomic orbitals together to get a new bond, I get a lower energy bonding orbital, but I also get a higher energy antibonding orbital. And that antibonding orbital isn't occupied, but it is a place where electrons could go if they became available. Filling an antibonding orbital breaks a bond. You've seen this before in the 351 substitution reaction, where you learned to draw that if you had an electrophile with a leaving group, a nucleophile could do a substitution reaction and break the bond. And you learned, by the way, that the SN2 reaction happens via backside attack. The reason for that is the antibonding orbital of the carbon-chlorine bond actually points in this direction. So when you drew this arrows previously, you actually were drawing what organic chemists knew all along, which is a nucleophile dumps its electrons into the antibonding orbital associated with the carbon-chlorine sigma bond. When you fill an antibonding orbital, you break the corresponding bond. Okay? We don't have time to talk about it in a lot more detail. If you've been with some of my colleagues or me for 351, this might sound familiar. If it doesn't, go check out that optional MO theory study guide. Skip all the nerd math and just get to the part about the antibonding orbitals, and you should be good to go. For the carbonyl molecule, the LUMO, the lowest unoccupied molecular orbital is what we're going to call the pi star. This is the antibonding orbital associated with the pi bond. How do we know it's the lowest energy orbital? Well, pi bonds are less stable than sigma bonds are, right? A pi bond is higher in energy than a sigma bond is. In a similar way, the pi star is lower in energy than all of the sigma star antibonding orbitals. And again, if you want to know more about that, you should go to the review study guide and check it out. What does the pi star look like? We'll take a couple of different views of it. I'm going to draw the aldehyde again. Here's the overhead view, and then here's the view of the aldehyde from the side, sort of occupying this plane with the carbon-hydrogen bond pointing out at us and the carbon-carbon bond pointing away from us, and the carbon-oxygen bond in the plane of the page. If we were to look at this antibonding orbital, I'm going to draw it. here, there is a lobe of the orbital on the carbonyl carbon, another lobe of the orbital on the oxygen. The lobe is actually bigger on the carbon than it is on the oxygen. There is a node in between the carbon and the oxygen. The node is a place where electron density, or wave function squared, goes to 0. We're going to use color for different wave function signs of the molecular orbital. The sign switches because the wave function goes to 0 in between the two. There's another node in the plane of the carbons, in the plane of the sp2 hybridized carbon, and so there will be lobes below the plane of the page as well, with a change in wave function sign there. I'm using color to indicate sign of the wave function. If we were to draw this orbital over here, there would be a large lobe on the carbonyl carbon and a smaller lobe on the carbonyl oxygen. Again, a node in between the two atoms where wave function goes to 0. And then we'll use color, again, pink and orange, to indicate switches in wave function sign. That's what it would look like. Sometimes that drawing isn't helpful to people. So we'll go to another program called Spartan, where I will draw a carbonyl for you. Just a simple aldehyde. Oops. That wasn't it. By the way, I've spent probably the equivalent of multiple years of my life waiting after a child has done something and said, wait, that wasn't it. So if you have to spend a lot of time with me erasing things and say, wait, that isn't it, I'm just preparing you for your future. Anytime a child wants to show you a trick on a trampoline that they've already done and then you show up to watch it, it is a guarantee that the next 15 minutes of your life are going to be taken up by someone telling you, no, that wasn't it. So if we look at what the LUMO of this molecule is, just going to turn it off again. Here is the carbonyl carbon in gray, oxygen in red, hydrogens in white. You have a large lobe on the carbon, a small lobe on the oxygen, a node in between the two nuclei, and then the side view shows you there's a node in the plane of all the atoms. This is the lowest energy empty orbital for this molecule. And when a nucleophile attacks, it's going to attack to put its electrons in the lowest energy spot that's possible. Let me show you how this works for a carbonyl molecule. Here is a nucleophile. We're going to be generic about it. Something with extra electron density. It's going to dump its electrons into the LUMO, into the pi star. Notice that the LUMO is on both the carbon and the oxygen. Why do you think it goes for the carbon instead of the oxygen? Because the carbon has that partial positive charge on it, right? Now, what happens when I fill an antibonding orbital? What happens when I fill a pi star? The pi bond has to break. So if you know what the orbital is and you have the nucleophile dumping into that orbital, the next arrow you don't have to memorize. It just comes out of that analysis automatically. You have to break the carbon-oxygen pi bond. Those arrows then become the instructions for drawing the next intermediate in this reaction, which was a nucleophile attacking the carbonyl compound. Now notice that nucleophile attacked. I went from a carbon here that was sp2 hybridized. Now my carbonyl carbon is sp3 hybridized. Because of that, we are going to call this intermediate, which you predicted, based on your understanding of carbonyl reactivity, we're going to call it the TI, or the tetrahedral intermediate. This is a common intermediate in all the carbonyl reactions that we're going to talk about. You need to be paying attention to the idea that a nucleophile attacks at the carbonyl carbon to give you a tetrahedral intermediate. Okay, I have 1 minute left, and we need every minute desperately this semester. So I want to do one more thing, and that is ask you how this reaction might be different if instead of using the aldehyde, I used the acid chloride. Now remember, the acid chloride's about as reactive as the aldehyde, but the difference is you got the chlorine on there, and you know chlorine's a good leaving group. So by analogy to what we did with the aldehyde, nucleophile attacks the LUMO on the acid chloride, you should get a tetrahedral intermediate. What do you think is going to happen next? Chloro is a leaving group. The next thing that can happen is called the collapse of the tetrahedral intermediate. Electrons on the oxygen can kick back down, break the carbon-chlorine bond. We could analyze the orbitals here if we wanted to. I found it generally not necessary to help students to understand this chemistry, so I'm not going to. If you want to know more, feel free to stop by and we can chat. Leaving group leaves, and you end up with this, which is a substitution product. Okay, that's the beginning. You have a study guide for chapter 13 that you need to start working on. Good luck, and I will see you Friday.